Hey guys, welcome to day 39. Nice job with the related rates. A lot of good work done there. A lot of us demonstrated that standard. If you weren't able to, didn't pass it, it's all right. We'll take another crack at it because it's a good skill to have mastered. Today we're going to look at something which I think is a much easier topic than related rates, and that's local linearity. So if you just look at that term, local linearity, right, we see linear in there. Basically, the idea here is that if we look at a curve, like a function f that's curved, when we really look at it closely in a small area, it starts to behave kind of like a line. And we can use that to estimate unknown values of f by using a tangent line approximation. So here's what I mean by that. So again, here's a curved function f of x. And again, you can tell f of x definitely does not look linear, right? It's clearly got a curve to it. But if we zoom in really close, it starts to behave a little bit more like a line. For example, if I focused on just this little section right here, again, I can still see it curves a little bit. But if all you saw was that little piece, it's going to look more like a straight line. If you think about the planet Earth, right? We always talk about being on flat ground, right? And there's a lot of idiots out there who think that the Earth is flat. Okay, but again, the Earth is more like a sphere, but when we're zoomed in on just a little patch of Earth, it feels like it's pretty flat, right? Same idea here. So what we're going to do then is we're going to be able to estimate values of f of x near a point we have by looking at a tangent line. So here's how this works. So again, I'm just going to show that zoomed in piece. Okay. So here's f of x. F of x is definitely a curve, okay, but we're zooming in so it looks pretty much like a line. We focus on one point here. This right here is a known point, x comma f of x. Maybe it's the point 3,5, maybe it's the point whatever. Okay. Now if we sketch a tangent line, okay, what we're going to see is the tangent line is going to run really close to, I'll use a different color for the tangent line, I'll use red. If I sketch a tangent line here, so in red here is a tangent line. The tangent line also has the point x comma f of x. What we see here is really close to that point, x, f of x. If you can see, the red line and the black line are almost on top of each other, right? So if I wanted to make a guess for a number just a little bit to the right of x, but I don't know f, instead of plugging it into f of that, I can just plug it into my tangent line, and I'll get a pretty good approximation of the actual value of f of that number. Okay? So what I'm doing here, right, I'm going to guess this number. Let's call it x plus h, f of x plus h. Oops, f of x plus h. I'm guessing that black number by plugging that number into my tangent. And then I just have to find the y value in that tangent line. And what you see is they're not going to be exact, but they're going to be really close to each other. And the closer I choose to my x value, the better my approximation of that tangent, my approximation using the tangent line is. Okay. In order to do this, I'm going to need to know that point, and I'm going to need to know the slope of the tangent line. Okay, so let me show you what problems like this can look like. Okay, so here's the problem. It is known that f of 3 equals 7 and f prime of 3 equals 4. What we want to do is we want to estimate f of 3.2 using a tangent line approximation. Now, since I don't know the function f of x, right, I can't just plug 3.2 into my function f because I never had a function f to begin with. So for me to figure out what an estimated value for f of 3.2, what I'm actually going to do here is write the tangent line, and then I'm going to plug 3.2 into my tangent line. So again, going back to our picture here, this is like the point 3.7, and I want to know this point, which I'm going to call 3.2, comma, blank. I want to know what that is. But since I know the slope of this tangent line, I can write an equation for this tangent line, and I can plug 3.2 into my tangent line, and that will give me a y value, and that'll be my best guess of the y value here. Okay, that's what we're doing. Okay, and doing this is very simple. So the first thing I need to do is write an equation of a tangent line. So to write an equation of a line, I need a point and a slope. My point is given right here. I know my point is the point 3.7. And my slope of the tangent line is given right here, which is 4. So what I can do now is write the equation of the tangent line. Very simply, I can say y minus 7 equals my slope times x minus 3. Then to estimate f of 3.2, again, this is an x value. I want to plug that x value into my tangent line equation to figure out the y value in the tangent line. And that's going to be my best guess then of what f of 3.2 is. Now, it's not going to be perfect, but it's going to give me a pretty accurate idea of what it is. So, watch how we do this. I'm going to say y minus 7 equals 4 times, and again, I'm plugging in the value that I'm approximating, which is 3.2. And now, without a calculator, I just got to solve this thing out. So I'm going to get y minus 7. 3.2 minus 3 is positive 0.2. So then I got to multiply these together, and I'm going to get y minus 7 equals 0.8. Then I just got to solve for y. I'll add the 7 over, and I'll get y equals 7.8. Now, that is exactly the y value on the tangent line, right? That is exactly this number up here, which is going to be our best guess for what that y value is in our function f of x. But it's not exact, and when we write this, we need to show that this is not an exact answer, this is an estimation. So the last thing we have to do is this. Therefore, f of 3.2 is approximately 7.8. Okay, and that's it. And I think we'll just cut it there. A nice short one. We'll go in a little bit more depth tomorrow during class, but I want to give you guys a chance to see that on your own and make your own conclusions. So that's it for today. 2 trains. Bye.